the sort of irritating and uninteresting features that you need to make a secure system. It only has the guts of the encryption. So it's the sort of thing mathematicians like to analyze, but in reality, you have to do more to be safe. All right, so we got 5, 6 people back. They are coming back. All right, let's carry on here. So, oh, I should mute them so they don't annoy one another. All right. All right, so there's this crazy Galois counter mode, Galois or something, I don't know how you pronounce his name. And the idea here is you're going to add a message authentication code to it. We're going to see more of these MACs and HMACs. They're used in financial transactions a lot. So you have not only encrypted text, but then you add a signature of sorts to it so you can detect if it has been changed. And that's the game here. This proves, typically it includes a shared secret. So you know that the only person that can make that signature is the authorized author of the message. And this verifies who it came from. The encryption itself does not verify that if you suppose that somebody got the key or cracked your encryption. So that's the game. It ensures authentication and integrity. And here's how it looks. You take all this junk together, you combine the plain text and the ciphertext and various other data, you feed in some authorization data to prove who you are, and then you create this thing at the bottom, which, let me see if I can get this sharing stuff out of the way. All right, there it is. This is how you make the auth tag, which appears at the bottom. Let's see what this is saying. The only one with no audio. Oh dear, is there no audio? Well, there should be audio. It's not mute. If you have no audio, that's annoying. Let me check my audio settings. He did? Okay, yeah, I think you must, I hope you're the only one. Let's see, perhaps someone else says something. I can hear. Okay, good. I guess the audio is working. It's just Richard. Turned off your speaker or something. All right, good. Good. Well, I appreciate you guys sending chats about these things. Since there's so many remote viewers, I would like to, rejoin. Okay, good. All right. So, anyway, let me make this thing as big as I can where it doesn't ram it in. And you see, that's how it makes its authorization tag. It feeds in information, including this authorization data, so you know who it is.
Question.
Yeah.
So there is one more counter 3. Does this change the expand?
Yes, yes. It's not that it just does the first 3 blocks, it does all the blocks. So the authorization tag verifies not only that you know who sent it, but the entire message is intact.
The next guy is going to be the last, for the counter 2, the last about going to the next part.
Yeah, I'm not sure exactly what the diagram will look like, but it includes everything. So each block is going to be included. All right, and let me make sure these guys are muted. Thought I heard a funny noise. All right. So, all right. And so now we can talk about key search. Remember, the problem with DES is you have a 56-bit key, and it can try them all. In AES, you have a 128-bit or longer key. And both of these have the effect, of course, that there's only one right key. And people don't even talk about this, but I always wondered about this. If you're doing a brute force attack, trying millions of keys, how do you know when you've won? You end up with some random looking junk. Typically, the way you know you've won is you can read it because it's in English. But that's how do you automate that? And I think you look at things like the entropy, you look at unprintable characters. But there are cipher schemes like the one-time pad that are completely unbreakable for this reason. The one-time pad has no pattern in the key bits at all, and you XOR them at the message. So if you try all possible strings of key bits, you will produce all possible results. It's like the monkeys creating Shakespeare by hammering at a typewriter. You will find every possible message, including many that are perfectly readable. And so there's no way you can tell when you've won. You can do a brute force attack, but you can't tell which one is the right answer. So the same thing can happen here. If your cipher actually has a longer block size than a key size, then there's more than one key that deciphers the block. And this happens for DES. There are 2 to the 64 possible blocks, but there's only 2 to the 56 possible keys. So it can happen. Anyway, there are certain cases in which that happens, but it doesn't happen for AES, and all the others aren't that important. It's just a thing to be aware of. This is an issue And the point in your book was it can take a second pass or more blocks of data to discriminate between which of the possible keys is the right key. All right. And then if you want to increase the security of the block cipher, there are already 3 levels. So you can choose 128, 192, or 256 for AES. And there is nothing wrong with any of them as far as we know. The only reason the longer blocks exist is to future-proof it against quantum computers. And so if you want to increase the security, you could just have more rounds of encryption with more keys. That would seem good. Or you could have key whitening, where you just add more keys to the existing encryption. And both of those tend to work. But multiple encryption turns out to be a lot less useful than you'd think it would be. And this is why we have triple DES instead of double DES. So that's the cute thing here. This is why double encryption does no good. It's the meet in the middle attack. So suppose you have double DES. You're going to encrypt with a key 1, key left, and then you're going to encrypt again with key right. So you would think it would be more secure, but it's not, because you just meet in the middle. You do a brute force attack on the first encryption to get halfway through, and you save all those answers, all 2 to the 56 of them. Then you do a brute force attack from right to middle and find the middle that matches. And when it matches, you found both of them. So it turns out that it only takes twice as long as brute forcing a 56-bit key to brute force both 56-bit keys, because there is a way to stop in the middle. And the same thing would apply if your encryption routine had some way to stop in the middle. And there is another cipher called A4. There's a whole series of them that fell to attacks like this, when you split them in half, and that takes you to the square root of the number of guesses, not just half the number of guesses. So that's the game here. So it takes 2 to the k+1 operations. So so 2 DES is only 1 bit stronger than 1 DES. Yeah. Yeah, but this is why, because you have the meet in the middle attack. And obviously, even single DES would be no good if there was some way to cut it in half. So when you make your series of rounds and rounds, you have to make sure there isn't some way to split it into pieces and meet in the middle. So you brute force the left half, you saved all those results, then you brute force the right half and hunt for a match. And so you end up having done only 2 to the k+1 encryptions, plus some other operations, plus using a lot of memory. I mean, it's not completely free, but it is possible.
Could you use the same kind of thing for the regular, kind of brute force regular encryption?
Yes, the question is, can you do the same thing if you brute force regular encryption? And you could, if the encryption algorithm somehow has a spot in the middle that you can approach from both sides. And so they carefully arrange them so that the way the rounds work, you can't do that. That's the trick here. So that's why making one encryption routine with twice as many rounds is what you did with AES.
What do you mean? What do you mean you have to split it? You mean you have to get the data in the middle of it?
Yes. You have to somehow be able to do half of it and save that result. And then do half backwards and save that result. That's why this works.
No, I mean like AES 128.
Right. That's a big issue. If you have AES 128, if there was a way to calculate half of AES and then do the other half backwards, this would work. And AES 128 would only be as strong as 65 bits. So they designed the algorithm to prevent that.
Could you just do half of it and say the result and then do the other half and then see?
No, and that's the point. In the design of the algorithm, even though it has a lot of rounds, the rounds have to go forward and they can't easily go backward. That's why you do it that way. It's carefully designed. This is a big issue, and that was what was wrong with A4. There was a way to go halfway through it and stop. Yes, there are these 10 rounds. If there was a way to do 5 rounds forward and then do 5 rounds backward and meet in the middle, it would fall. So when they design it, they connect the rounds together in a way to prevent that. That's an important issue of design. And that's why just taking 2 DESs and putting them and repeating it is much worse than making a new version of DES with twice as many rounds. Would be a lot safer. That's the problem. Something that can be split in halves is the fundamental error here. And so that's why they do triple DES. The whole point of triple DES is you've got 3 rounds, so you can't cut it in half. All you can do is cut it into 1/3 and 2/3. So now that attack requires 2 to the 56 bits, brute forcing 2 to the 56 here, and brute forcing 2 to the 112 over here. So that's why I've always wondered this. They say triple DES is effectively 112 bits of security. Why isn't it 3 times 56? And this is why. It's effectively 113 bits of security. And that's cute. So that's why an odd number is good here. And if you made quadruple des, it would be no better than triple des. So that's against this particular attack. All right. So that's the game. Triple encryption, because you can't split it in half, you're now as strong as 2/3 of the bits. All right. So that's the game. Another thing you can do is key whitening. We've talked about this. You're going to encrypt something with a key here, and you're worried that that's not strong enough because this is something miserable like single des. So you XOR it with a 64-bit key here, and you XOR it with another 64-bit key here. And that just means they have another 128 bits they have to guess. And that means the brute force attack is greatly slowed down. So that's done there. DESX is the version that does this. It actually uses predicts key 2 from key 1, so it really only adds 64 more bits, but adding 64 more bits to 56 is enough to make it essentially unbreakable. And AES already includes key whitening in the rounds. There was a round of XORing and a round of XORing at the end. They already built this into the system. All right. So the big wild card is quantum computers. The NSA has warned us all. Quantum computers are coming. The algorithms for quantum computers were designed in the 90s. People figured out what they could do in principle and how fast they would be if someone knew how to build them. So the algorithms are out there. Grover's algorithm can calculate. And the trick about quantum computers is they can get to the answer without doing all the calculations. They can try 2 to 128 keys with only 2 to the 64 calculations. That's why they're fast. So that's why AES has 192 and 256-bit modes, because even half of those bits is still secure. So it is possible that AES 128 will be broken by quantum computers, but it is not apparently possible that it ever breaks AES 256. Yeah?
Sort of aware to me of how quantum computers work, like qubits, how they can key or state.
Yeah.
You can explain that some more.
Well, I can only, the question is, how do quantum computers work? And I can tell you only in I can tell you in simple terms. See, the simplest quantum computer calculation I know is protein folding, but ice is the same. You have a bunch of water. The molecules are just running around at random. Then you cool it. Then suddenly it crystallizes into ice. So all the atoms wander around until they find a place to be where they make a crystal. And then they line up. And the way they find it, quantum mechanically, is atoms are not just in one place. They smear around like gas. It has a probability of being here and a probability of being there. So they sort of feel their way to the right spot without, now the way a digital computer would do this, it would try one position, try another position until it found the right place to put the atom. But quantum computers just sort of smear out and condense. And that's so that they effectively explore many options really fast in parallel. Each atom is like a computer. Each atom feels around all the places it might go and then goes to the right place instead of trying them one by one, which is how a digital simulation would go. That's the trick. And it is a little bit goofy, but it has to, the reason why this actually is faster is because it really is true of reality that atoms don't have a physical place. And they have these mystical things called de Broglie waves that go out faster than light and probe the world deciding where to go, which just sounded like madness when they invented it all around the turn of 1900s, but it turned out to all be true. So this is just a more clever way of using atoms than the way we do it now, which is making a transistor and calling it one bit. If we actually use the electrons the way they are, as the quantum mechanical uncertain objects they are, they could do computations much faster than this artificial thing where we take 1 million electrons here and call that 1 and there and call that 0, and then shove them around in large quantities to try to make them digital when they were analog in the first place.
So they don't use binary math?
They don't use binary math. They use qubits. Instead of having bits, you have qubits, and a qubit just has a probability function, a chance of being 0 and a chance of being 1. And they're uncertain and they're entangled so that when you cool them down, they settle into the answer state. There used to be a thing called analog computers. Long before there were digital computers, if you wanted to make a thermostat, instead of taking a thermometer and getting a number for the temperature and then a number for the desired temperature and calculating how much heat in, you just made something where you had a needle set, and if this needle falls down, it applies more voltage to the heating coil. And the more this is wrong, the more it turns on the heating coil. You know, that's analog devices, you know, get more value out of the hardware because the hardware really is analog.
So bear with me, like, what
Yeah.
size, I guess, breaks the symmetry of like 1 or 0 with the size
What's the what?
So you're showing a code bit, so it's either 1 or 0.
Yeah, you don't have that anymore. What you have is you have it in an uncertain state that has a probability being 1 and another probability being 0.
What terms are called?
The temperature, which you feed in sort of randomness. If the temperature is high, they have an equal chance of being 1 or 0, and then you cool it, and it freezes down into its stable state. And you arrange it on a surface so that it will freeze into the surface that's the right answer. That's the trick. So writing the program is really bizarre now. Writing the program is creating associations among the qubits that favor the right answer. And then you feed in some randomness and you gradually decrease the randomness so they cool down. It's a completely different process than digital computation. It doesn't go through steps, do step 1, do step 2, do step 3. It's just like, you know, making funny shapes of ice. You make a tray that will cause it to make the shape you want, and then you cool it. Yeah.
For the same ciphertext, it's going to be same entry?
The same what?
For the same ciphertext? Can you switch to the quantum computer? Same entry?
No, I don't think so. You do not have to be in electronic codebook mode. No, your quantum computer can run any algorithm. You program it with the association between the qubits. So it could do any of these modes, I think. But I'm not really sure about that level of detail. Anyway, none of this is all science fiction right now, although there's been clues that the NSA has it working. Yeah.
There was a company, I believe, called D-Wave that maybe sold quantum computer prototype to Google.
D-Wave, I think, yeah.
And the question that I have is this. Apparently, they had to work on proving that it's actually faster than a regular computer. So
yes.
Why would it be uncertain whether it actually works or not?
I read about either the G-Wave or the Q-Wave. Google has something. There was a huge argument that wasn't really a quantum computer at all. The only case where this effect is known to absolutely work is when you have things like photons near absolute zero. When you cool matter, it's very expensive. Then you can make like 2 qubits and show that they're associated. But there are commercial devices that claim to have something like 4 qubits. But it turns out they're not perfect, and they're not perfectly associated with each other. And so the question is the entanglement among them good enough to get anything done or not? And so that's the problem. To get anything close to perfection, you have to be really near absolute zero, but that makes it super expensive and crazy. And none of them yet are faster than classical computers at anything. They don't actually outperform classical computers until you get up to, I think, 16 or 32 qubits. And nobody's made more than 2 or 4. So the hardware problems are large. But
they're working on 50 qubit.
52-bit?
50 qubit or something.
Okay, fair enough. So eventually they'll have prototypes that are actually faster than a classic. Right now, there aren't any though. Right now, it's all just proof of concept, very simple systems, solving ridiculously simple problems like tic-tac-toe, but showing that they did it the other way. So it's not an immediate effect, but apparently the NSA thinks that we will have it functional by 2030. That's when they're worried about it. So I got a few more cahoots about this, and then a little bit of math. So this is going to be 5B. Let's try having the right one this time. All right. Because having to answer the wrong questions is a little too difficult. All right. 979, 915. I got 14 online and 8 in the room. Seems like some more people might want to join. I'll wait a few more seconds and then give up. I may have abstainers. All right, I got Kahoot abstainers. All right, so. Okay, which mode computes a Mac? All right, that's Galois counter mode, makes a message authentication code. All right, what cipher allows many different keys to decrypt the same block? Yeah, it's none of them. I think I said in lecture mistakenly DES has the property, but it doesn't. It's only going to happen when the key is longer than the block. So there are more keys than blocks. So if you have a 128-bit key and a 64-bit block, this would happen. And there are some goofy ciphers like that, but none of the important ones we care about. Anyway. All right, what levels of AES are safe? Right now, they're all fine. There's no known attack against any of them. All these attacks are guessing about the future. Yeah.
So many different keys will be for the same block if the key is longer than the block.
Yes, if the key is longer than a block, then you have more keys than there are blocks of ciphertext. So more than one key. It's sort of like a hash function then. You have a long thing turning into a short thing. So there are many of these long things that map to the same short thing.
So in that case, wouldn't AES count because all the keys are going to be like AES 256? But it's longer than a block, so.
Well, actually, that's interesting. I don't know the answer. I don't know what the block size is of AES 256.
16,
I think it's still 16 bytes, isn't it? Then I think you might be right. Maybe AES 256 falls in this category. That's an interesting point, and I didn't think of it.
Also AES 192.
Also AES 192, if you're right, I think. Kind of screwy. Yeah, anyway, all right, we'll keep going. All right, so what method is rendered useless by meet in the middle? All right, double encryption is the one that splits in half, and meet in the middle breaks it. So what does a meet in the middle? Missing a verb or something. So what does it have that a brute force attack doesn't? Oh, what does it require? That's what's missing here. What does a meet in the middle attack require that a brute force attack does not? All right, and it is much more RAM. Let me just make a note. Question 5B, require. Whoever wrote these questions should be demoted. But you need much more RAM because you have to remember 2 to the 56 calculations in the middle and try the other half. So it's much more RAM required, or much more storage of some sort. All right, so what technique can break RSA even for long keys? I think this must have been on a slide and I skipped it. We'll talk about it now. No, it's quantum computers. This is a big problem, and the public key encryption is very vulnerable to quantum computers. AES is not. The AES has 128 bits of key and it's just random. But the thing that makes RSA difficult is the factoring of prime numbers. And there's a strong evidence that that is going to get much faster. And RSA, even with much longer keys, is going to fall. So public key encryption is more fragile than private key encryption. And currently people are worried about that. Anyway, all right, so I got Eli and Japanese and Cam. So I know who Cam is. But Eli and the fellow in Japanese will have to tell me who they are, although I think this guy might be Lucky. I think I'm going to go with assuming this is Lucky. I remember he told me before. All right. And I do have another topic, hopefully with less mistakes in it. But let me go back and see if we did say, yeah, I forgot to say it, but here's the point. RSA will become insecure because for a quantum computer, it just moves you down to the square root. From 228 down to 64. So if you go up to 256, it's down to 128, and that's too many. But for factoring a prime number, exponential time that goes up turns into polynomial time, and that is an enormous change. So doing something, so if doubling the key right now would multiply the difficulty by an enormous factor, but then now doubling the key will only increase it by a much smaller factor. So it makes it much more dangerous. So people are very concerned that the RSA is going to be completely useless in 10 or 20 years. And AES should remain stable forever. So it's an issue. Yeah.
What about elliptic curve cryptography? Is that also vulnerable to quantum computing?
People, the question is whether elliptic curve is also vulnerable, and people are currently trying to figure it out, but the NSA has said yes. The NSA announced about a year and a half ago that they should quit using their recommended levels of all public keys and instead about triple the length of all the keys right now for both elliptic and RSA. I didn't hear what they said about El-Gamal, but I think nobody's using El-Gamal anyway. But I think currently people are afraid that all the algorithms will fall, although I'm not sure that there is a known quantum algorithm to do them. They're afraid they're all going to fall. And they're currently having a contest to pick quantum-proof encryption routines. And that's going to go on for maybe 5 years. So they're hoping people will come up with new systems that are more resistant to quantum calculation. Yeah.
I just know that there is a way how to poison elliptic cryptography, which was proven.
Right.
So that was a big concern. Like if NSA would approve it, what if they did it with some poison?
Yes, and that's another issue, but you're quite correct. That was shown, the version of elliptic curve that RSA built by default into their products was poisoned by the NSA, and they bribed RSA with $1 million supposedly to do it, and then they had to withdraw it because it has some numbers you feed in, and they chose them and didn't explain them, and it turns out that if you choose the numbers and they're related to another number, they can predict them. So yes, that's another issue. ECC is apparently susceptible to that poisoning attack, which also makes people nervous. All right, so anyway, let's do a little bit of modular arithmetic. I tried doing this before and we hadn't built up to it, so hopefully it'll be more clear now. So in good old modulus 9, we've done this a lot. Remember, 0 goes to 0, 7 goes to 7, and 10 means you've gone 9 is 0, 10 is 1, 11 is 2, you just go around the clock. So you take the number and divide it by 9 and take the remainder, and that's the modulus. So now if I do multiplication, 2 times 9 mod 9 is 2 mod 9 times 0 times 9 mod 9, which is 0. And so you get 0 as the answer. 2 times 10 mod 9 is 2 mod 9 times 10 mod 9. That's 2 times 1. That's 2. You could also do it the other way. You could take 2 times 10 and get 20, and then look at the clock. That's going to go around twice for 18, and you have 2 left over. So the answer is 2. So multiplication distributes this way. So try this one. 2 times 5 mod 9 is 10 mod 9, so that's 1. So that means 5 is 1/2. That's where you get a sort of mental, 5 undoes, if you double something and you want to undouble it, you multiply it by 5. 5 is 1/2. And you don't talk about division and you don't talk about fractions because it doesn't exactly make sense. The technical term is that 5 is the multiplicative inverse of 2. If you multiply by 2 and you want to undo it, you multiply by 5. And as you can imagine, this is going to be at the heart of RSA because this is how RSA works. You take the key and you multiply by the key, and to decrypt it, you have to multiply by the inverse, which is just another key. So if you encrypt by multiplying by 2, you decrypt by multiplying by 5. And that will get you back where you started. For XOR undoes itself, but things based on prime numbers and ring arithmetic work this way. You do want to have some way to get back where you started, but there is no division, so instead you multiply by the inverse. And this inverse does not always exist, but it has to exist for the ones you're really going to use. The encryption routine, you have to choose numbers and ring sizes such that there is an inverse, and you have to find the inverse. All right. So let's try modulus 9. 6 times 1 is 6. 6 times 2 is 12, so that's 3 past 0. 6 times 3 is 18, so that's 0 again. 6 times 4 is 6. As you can see, since 6 and 9 share a factor, common factor of 3, all I'm doing is 630, 630, 630. There is no inverse. If I were to encrypt by multiplying by 6, there would be no way to decrypt. I would just destroy information. So that's an issue. And that's why they talk about relatively prime. You can only decrypt if the key and the modulus are relatively prime. They have to share no factors in common. If they do, then you're not really going to hit all the numbers as you're going around and around. You're just going to hit the same numbers over and over. All right. Let's see if I can get this thing to, who cares? All right. So let's try 7. 7 times 1 is 7. 7 times 2 is 14, which is going to be, whoa, modulus 9. 14 is 5. 7 times 3 is 21. That's 18 plus 3. That's 3. 7 times 4 is 28. That's 27 plus 1. So 4 is the inverse of 7. If you encrypt by multiplying by 7, you decrypt by multiplying by 4. Okay?
Can you give some examples of how you multiply by 4 and reverse it?
Well, take this one. If you take a number like 1 and you encrypt it by multiplying by 4, it becomes 4. To decrypt it, you multiply it by 7, and it becomes 28, which is 27 plus 1. It works. It may seem insane, but it does work. And the reason it works is because you can group the multiplication. Let me just try drawing it here and see if I can make it more clear. So I have I'll have my plain text. Let's encrypt the number 3. Then I multiply it by 4 to get the ciphertext. Now to decrypt it, I'm telling you I'm going to multiply that by 7. Okay? Let me do this times 7. Okay, so that's what I did. This stuff here is the ciphertext. This is the decryption process multiplied by 7. Now, the reason it works is because it commutes. So you can write it this way. And this number is 1. That's why it works. So if you have the plain text here, and the key is up here, this is the key, this is the decryption key. And that's why it works, because you know you choose the key and the decryption key, so they're 1, and that gets you back to the plain text. That's why. The encryption process goes this way. The decryption process does that, but that means the overall result is to get back to the plain text. All you're doing is the same multiplications out of order.
So 3 times 4 mod 7 is 5?
Right, 3 times 4 mod 7 is 12, that's mod 9. This is all mod 9.
Oh.
Yeah, so 3 times 4 is 12, so mod 9 is 3. And so that 3 encrypts to 3. And 3 times 7 is 21, which is again 3. So it's not a very brilliant chase. Let's try encrypting 2. So it's more clear. All right, let's get rid of this junk. Okay, let's try encrypting 2. So 2 times 4 is 8. So the encrypted ciphertext here is 8, and you multiply it by 7, you get 56. And that's 54 plus 2. So it is the case that if you encrypt by multiplying by 4, you can decrypt by multiplying by 7. You do end up back where you started. It seems nuts, but it's not. And if you want a real mind bender, when we get to discrete logarithms, you will see that you don't even need to think in these mathematical terms at all. It's just a way to map one set of numbers to another set of numbers. That's all that matters. And then you have another way to map them so they go back. But that's all right, we'll get there. So let's see if you can do a few more of these. We'll see how you like it. So here's modulus 4. So 0 is 0, 1 is 1, 3 is 3, 4 is 0, 5 is 1. We're going around. So now 12 mod 4 is 0, and 13 mod 4 is 1. So hopefully that's clear enough there. And I didn't put a multiplicative inverse here, but we ought to talk about it. Suppose I want the multiplicative inverse of 2. If I take 2, 2 times 1 is 2, 2 times 2 is 0, 2 times 3 is 2, 2 times 4 is 0. I'm never going to hit 1 or 3, so 2 has no inverse. But 3 has an inverse. 3 times 1, go forward again, 3 times 2, 3 times 3 is inverse. So 3 is its own inverse. It decrypts with the same key that it encrypts with. That's also allowed, okay? And that's because 3 times 3 is 1. It's 9, which goes around twice and gives you 1. Okay? see puzzled looks out there. But that's, let me just put it here. Controls tab, that'll do it. Yeah, so 3, let's put it over here. So in mod 4, there's this 3 times 3, mod 4 is 9, mod 4, and that's 1. So that means if I take anything and multiply it by 3 to encrypt it, I just multiply it by 3 again to decrypt it. Just like XOR. You do the same thing again and it undoes itself. So if I take 2 and I multiply it by 3 to encrypt it, I've got 6. If I take that mod 4, it's 2. And if I multiply it by 3 again, I'm obviously going to get 2 again. So let's take 3 and as the plain text and multiply it by 3. That gives me 9. Mod 4, that's 1. Okay, so I multiplied it by, right, and now if I multiply it by 3 again to decrypt it, I'm going to get 3. 3 is my plain text. So again, this is the plain, and this is the key, and this is, let's put it here, times 3. This is the decryption key, and this is the plain text again. There. All right, people look a little confused, but I hope you're getting, and I just hope it sinks in. We may do some repetitions of it. Let me see if you like the Kahoots, and we'll move ahead. If you don't like it, we'll keep going over it. This is the essence of public key encryption, this technique. Let's see how you like this one. Oh, let me restart the meeting. They're going to run out in 3 minutes. That's not good enough. I'm going to stop and restart the Kahoot. Stop, end meeting. That's correct.